Hey everyone, and welcome to the Printerview, a webinar on 3D printing brought to you by PLM Group. With us here today, we have one of PLM Group's 3D printing experts. His name is Christopher Wester, and he's here to talk about the fundamentals of 3D printing. Hi, Christopher, welcome.
Thank you, Matthias.
Now, Christopher, can you walk us through the agenda of today's webinar?
Sure. So today's agenda of this webinar is for everyone who wants an overview of what's out there in terms of 3D printing. So anyone who does a quick Google search gets something like this that you can see on your screen, I believe, right now. Yeah. So there are lots of different technologies, fancy names and stuff. So the goal of today is really to categorize each of these technologies and talk about the benefits and who benefits from it, and really what makes each technology special, really. So first off, the way we will rate each technology is by 5 metrics. So the first metric is capacity, and capacity means the build volume of the machine, the printing speed, but also the scalability of the system. So a low score here means a few products, and a high score means production, basically. The second metric is accuracy, so that incorporates surface finish, but also tolerance of the printed part. Third is ease of use or usage, so that means how much site preparation is needed to install the machine, how easy is it to use, how much extra equipment do you need, how much processing, post-processing is involved, and I mean ease of use of this as a whole. Next is cost. We won't talk about machine cost because that varies quite a lot between different technologies. So this is cost of operation, so cost of materials, service, yeah, stuff like that, not tied to machine cost.
Right.
And finally, we will look at materials. So the amount of materials for each technology, material properties, but also geometric limitations. So certain technologies allows for very complex designs, while some are limited in more ways, so to speak. So these are the 5 metrics we will look at today. And on top of that, when we're out talking to customers, we have identified 3 user groups that we'll focus on. So hopefully, for all of you listening, you can identify with at least one of these. The first one is the business owner. So from that perspective, from that user or that person, we look at costs, profit, maybe customer satisfaction, and business impact in general. The second role is the product designer or the engineer. So from that perspective, we look at prototyping, product design, functional testing, and so forth, more product related. And the third and final is more tied to production. So the production manager is looking at tooling, automation, lead time, and more production related topics, so to speak. Good. Yeah, so that's what we're going to look at. We have the ratings, we have the reference roles that we're going to look at.
Excellent. So now we have our ground to work from, right?
Yeah, correct.
So let's dig into the different technologies. And we're going to start off by asking Christopher to walk us through one of the most well-known 3D printing technologies out there. And we're calling this melt materials as a generic term for the different technologies in this particular technology group. So Christopher, melt materials, how do you define that, and what technologies are there in that group?
Yeah, so melt material means that you have a solid material that you then melt, basically. So, and I forgot to mention it in the beginning, we will look into 3 different groups.
Right.
The first one is melt materials, and we will also look at powder materials and liquid materials. Then each of these groups have like sub-technologies or subgroups that we will look into. So the first group under the melt materials is, I think, the most common, the most well-known. It's called FFF, fused filament fabrication. And that means, in short, that you have a filament on a spool.
Right.
You feed it up to a heated nozzle,
yeah,
like a glue gun, and then you print or extract onto a build plate, basically. And
right,
in that way, you build your 3D geometry.
So FFF.
Triple F, easy to remember. Yeah. So looking into what this is used for and what the benefits are with FFF, starting with capacity. capacity for FFF is generally quite low because of its low printing speed. It's like a mechanical system that needs to pass over the build plate and create the geometry. But it does have usually, or it can have quite a big printing volume, which increases the capacity somewhat.
Right.
The next rating is accuracy. Generally, it has the worst or one of the worst surface finishes out there, but it does have quite a good tolerance. So if you have a simple geometry that doesn't have like needs smooth surfaces, but it needs to fit well, this is generally a pretty good technology.
Right.
Next up is usage, and that is like the middle of this technology. The machines are like a low threshold, quite easy to install, easy to use. It doesn't require any extra space or ventilation or anything, easy to set up. So it's a very common first machine for people. Cost or operational cost is also quite low. You can get really cheap machines and also really cheap materials. And going to materials, it has quite a wide range of materials.
Yeah.
Everything from really cheap, like PLA and ABS materials, up to high performance, such as Ultem materials and carbon fiber reinforced materials. So
for specific mechanical properties, I suppose.
Exactly. Yeah.
Right.
Yeah. Exactly.
Yeah.
Yeah. So to summarize the metrics of FFF, really easy to get started. Very common first machine, low threshold, has a wide range of materials, but it prints slow, which makes it more suitable for prototyping maybe or low volumes. Pretty good tolerances, but it does have geometric limitations. So if you want to do super intricate fine detail parts, this is not in general the technology for you.
Good. Great.
Yeah, so that's the rating we put on FFF. And looking into who is the most common user and who benefits the most out of FFF, we have these three roles I mentioned before. So the ones who benefits the most are the product designers. They really love this for prototyping and product development. Really great for simple geometries and to get fast in-house low volume prototyping. Production doesn't benefit as much, but it can be used for production equipment, such as jigs and fixtures, if you don't have too high requirements on strength.
Right. Something you could use on the assembly line.
Yeah, exactly. Yeah. As long as like a tool that should lift stuff, because ABS or PLA materials generally don't have the high enough strength.
Right.
Yeah, exactly.
Yeah.
And looking from a business owner's perspective, it has generally a very low business impact. It's more like towards the product development or R&D areas.
Right. So if you want to buy a 3D printer without the boss knowing, an FFF printer would be your first choice.
Yeah. Low threshold, easy to get started.
Great.
Yeah.
Excellent.
So looking into some of the parts, and I will come with an example later. Looking at some parts from an FFF technology, this is kind of the surface finish you get from an FFF machine. So, I mean, it's not bad. I'm not sure if you can see it on the screen. It's generally actually quite okay, but a low rating means that it's much worse than the other technology. So this is not for you, but if you want higher, like better surfaces, you should definitely not go for this machine.
Right. Excellent.
So this is printed on one of our printers called Markforged. The material is a carbon fiber filled nylon material, really popular for actually for production equipment. So not only for prototyping and product development.
Great.
So a good example of an FFF application, especially with a Markforged printer that you just saw. You can click over there. We have a company in Sweden called Albin Components. And what they did was that they bought a Markforged machine with a capacity to print continuous carbon fibers. So if you can have a look at this one, you can actually see the fibers inside of the print, which makes this as strong as aluminium actually. So this is used for production equipment. So in the picture you can see there, it's used for like robotic grips, jigs and fixtures with higher strength requirements than just normal ABS prints.
Right. Yeah. And I suppose that type of technology is unique to the Markforged brand, right?
Yeah, exactly. Yeah. The continuous fiber is unique there.
Okay.
Yeah.
Good. Thank you.
So what they did, they invested in this machine, and then I visited them a month after the installation. And during the first month only, the amount of time they saved on their tooling department was 80 hours.
Wow.
And the amount of money they saved during the first month only on tooling was 4,000 euros.
Nice.
And also during, I mean, a very common thing for them was to outsource, obviously, to the workshops. And since they're installment, they haven't outsourced a single hour. So FFF with the right technology can actually be used for production equipment. So this is a great example of how to utilize easy to set up and great strength.
Nice, thanks.
Yeah. So that was the first, I guess, branch.
The first branch.
Yeah.
So shall we move on to the next?
Yeah, I think so. So the next one is also under the melt materials. It's called ADAM, which stands for Atomic Diffusion Additive Manufacturing.
Okay.
Which is basically an FFF technology, but instead of printing plastics, you have a plastic with metal powder bound inside. So you print it the same way as you do with the FFF technology, but the part then is made up of 80% metal. You then wash that part and you sinter it. So the part, the plastic burns off, the metal part.
You have a solid metal part.
You have a more or less solid metal part.
A high density metal part.
Yeah, roughly 95, 97% density.
No, it's interesting. Yeah. Okay.
So looking into the metrics of this technology, the ADAM technology, it has the lowest capacity, I must say. It has the same speed as an FFF, which is already slow, but then on top of that, you need to sinter and wash the part. So it does have quite a low capacity. Accuracy is also quite low, actually the lowest compared to all the other technologies because of the same reasons as before. Usage is also quite low because it involves several steps. So after printing, you need to again wash it and sinter it. So it involves more steps. So, but the benefits after, I mean, it is low capacity, low accuracy, not super easy to use, but it does have amazing material qualities because you print in a very easy, I mean, comparatively easy way with metal materials.
Yeah, right.
Running costs are, average in the middle. So just to sum up, the ADAM technology, it is the easiest way to start printing metal.
And everyone knows printing metal is one of the holy grails in 3D printing.
Exactly.
Lots of benefits, great value.
Exactly. Yeah.
Okay.
And previously, historically, it's been a really high threshold machine or a technology to be able to print metal, which is now easy.
Right, because of cost and handling, right?
Yeah, availability, I would say.
Availability.
Yeah, so machine cost is pretty low, especially compared to the other metal machines.
Yeah.
And it builds on this FFF technology, which is a really trusted platform.
It's been around for a long time.
Yeah, exactly.
Lots of users, of course.
Yeah. So really fantastic if you need metal parts without all the big machinery.
Right.
Yeah. But it does have a limited capacity. That's the main drawback. So looking into the roles again, who is the main user and who benefits the most out of this? From what we've seen so far, this is still a quite new technology. Production really benefits from this to be able to quickly produce one-offs such as production equipment, again, jigs and fixtures with even higher strength requirements, but also low volume production. And then I mean really low volume production.
Yeah.
It's quite well suited for that.
Right, like one-offs.
Yeah, I mean, it depends on the size of the print, but I mean, in the hundreds per year, I would say.
In the hundreds per year.
I mean, it depends on the size of the part.
So that's a good. Yeah, good.
Next up is the product designer. Again, this is great for prototyping in metal. So right now we can print in stainless steel, 74 pH, and tooling steel.
Yeah.
But as I said, it's still pretty new. So upcoming already in 2019 is another tooling steel and copper, and then coming after that is titanium and aluminium. So there are more, materials coming in the future.
There's a clear roadmap for new metal alloys and materials. Right, right. Okay. Yeah.
And looking from more of a business perspective, from the business owner's perspective, spare parts is a big thing. So to be able to reduce inventory and stock costs and have a machine print spare parts instead does save money for your business, basically.
Right, right. Thanks for that.
Yeah, and looking into how all these parts look. So this is a stainless steel part printed on this technology called the Metal X. That's the name of the machine. So you can see the surface finish and the quality of the part. Let's see if we can get it into focus. We can't. Oh, there
Almost,
it is.
there it is. Yeah.
So it's actually quite nice. This one has been slightly polished before sintering, which gives this nice surface. So you can have a look at that.
Yeah.
And you can also print, I mean, smaller details. It has basically the same geometric limitations as a FF. So in terms of size and tolerance and stuff like that. So this is a small M3 thread. It just goes to show how fine detail you can print. Focus.
Can we get the focus? Yeah.
Can we get the focus? No. You'll have to come and visit me, basically.
Yeah.
So really nice if you want a cheap way to produce metal parts, really, with 3D printing. Okay.
Right.
Some applications.
Let's see. There we go.
So this is a case from Stanley Black & Decker, a part that was previously made out of 4 parts and then assembled. It's part of an actuator housing for an outdoor tool. So by printing this, and all of these numbers are actually for production on an annual basis. So to be able to produce the actual part, year after year after year. Mm. So not too high volume, but they managed to get costs down by 41%. This specific part, the weight was reduced by half, which makes it it consumes less energy basically, and it's easy. Since it's a tool, you want the weight to be as low as possible. The number of parts again was reduced from 4 to 1. So part consolidation, making assembly non-existent basically.
Like no manual labor.
No manual labor, yeah, right. Exactly. Yep. So straight from the machine. And time savings is up to almost 70% to be able to produce a single component.
Right.
And this again is for annual production.
Yeah.
Looking at only one part, like they did when they benchmarked this, it's up to 95% both in cost and time savings to produce a single part. So great example on how to utilize the Metal X technology.
Excellent. Thanks.
Yeah.
Yeah.
And that actually sums up the melted materials, which is the first.
Right. Moving on to the next big technology family, I suppose, powder materials, which is another fast-growing technology family, I suppose. Indeed. Loads of brands out there, loads of different technologies. Please walk us through it.
Yeah. So looking at powder, we will look into two branches again. The first one is it's HP's technology, which has been around for a couple of years now. It's called MULTIJET fusion. And basically what it is, in short, is that you have a powder bed that's heated up. Yeah. Then you apply ink agents on top of it to create the geometry, and you apply extra heat to fuse the powder together. Then you take the parts out of the build bucket, chamber, the chamber, you vacuum it, and then you blast it, sandblast it. Yeah. Right. So this has been a huge hit since it launched a couple of years ago. Looking at what it's used for and its capacities. So capacity is the highest on the market. So this is a mass production machine, great for, it can compete with injection molding in many ways in terms of volume. So that's one of the main benefits. Accuracy is pretty good. It's around in the middle, so it's better than many, but there are technologies that's even better than this one. Usage, it does involve several steps. As I said, you need to cool the build down, you need to extract the parts, you need to vacuum it, you need to blast it, and then sometimes you need to color it or finish it up.
Right.
So there are many steps, but again, the amount of volume you get out of this is really amazing.
So all of those manual steps would actually affect the capacity somehow, but not in the way to affect the metrics or the result that you've given it.
No, not really. Yeah. So to sum up all this, if you look at the next metric, which is cost, it's the lowest cost of operation out there. Mm. So the cost per part is really, really low, even if you take into account all of these like post-processing steps, because of the machine's capacity and sheer capacity really. Yeah, it's really amazing.
Right.
Material properties is also really good. There are already a few materials out there. So you have the nylon materials, PA12 with glass beads, PA11, but there are many more materials to come for this machine. So to sum up really, the HP MULTIJET fusion, extremely high capacity, low cost per part, which makes it very suitable for production, obviously. Good material properties, but it requires both the site preparation with extra equipment, ventilation, control humidity, and the post-processing steps. So, you know, high stakes, but also high gains, I would say.
Right.
Really fantastic machine.
High stakes, high gains. So
Yeah.
that's a good sum up, I suppose.
Yeah.
Right.
So looking into the roles again, who is benefiting the most? And I would say the business owners. This really transforms the way you produce plastic parts. Reduces lead time, part costs. I mean, the supply chain, you do everything in-house. You don't need tooling. So this really affects the way you produce parts. And that goes to say also for production, obviously, many of the same benefits there, to be able to mass produce plastic parts without any tools. From day one, you can just start to produce parts.
Right.
But it also have a great effect on the designers, actually. So looking from the designer's perspective, you can create much higher performing parts, optimizing design. This technology allows for very complex designs. So we will have a look at a few. There are also some examples coming up. So
let's see if we can get this on the big screen.
Yeah, sure.
Bear with me here. And that should show there, but it does not. Bear with us, guys.
Did you click show screen?
Show screen.
Yeah, there it is. No, now you're showing that one, so you should stop it.
Let's see.
I think that's it.
Yeah.
So we're all new to this internet stuff.
We are. Some of us, most of us.
Yeah. So this is a part that just goes to show how complex geometry you can build, but also the kind of quality and finish you get out of the machine.
And this is printed in what material?
This is a PA12 material.
So PA12.
So nylon 12, a very functional plastic, really popular.
Or polyamide.
Yeah, exactly.
Right. Has a very nice texture and surface finish, which of course is very hard to convey digitally. You have to see it to believe it.
Yeah.
Yes, really, really nice. Great, thanks.
So you can really improve on product performance and product design as well. Not only the economical benefits, but also from an actual performance.
Right.
Really, really cool technology.
Great. Right.
So a good example of this is actually from HP themselves. So they are now printing many parts for their own 3D printers, actually. So this is a part from one of their machines. It used to be milled in aluminium.
Right.
It's a whole back and forth. It's some kind of cartridge. But they were able to reduce the weight of the part from 355 grams to 23 grams, which is like 95% or something.
Yeah.
And also cut the cost of this part in half. So this is, I mean, the amount of things you can do with this technology is really, really amazing, both in terms of time, cost, performance, everything. Yeah.
And just to be clear, this is of course an end-use part.
Yeah, exactly. So this is inside of their own machines, really.
Yeah. Excellent. Thanks.
Yeah. So that's the first powder technology. The second powder technology is metal powder, really. So instead of having this nylon powder that you did for the HP machine, now you have metal powder. And instead of using droplets and ink or agents to fuse them, you have a laser instead. So this is called DMLS, direct metal. And it basically, like I just explained, metal powder, laser, new layer of powder, fuse it with a laser, basically. Right. So this is also a really fantastic technology. Looking into the metrics and who benefits the most, capacity is quite high, but it's not the highest out there. It can't really compare to the HP machine, for instance, yet. Build volumes varies from really small build volumes up to much bigger, depending on how much money you want to spend on it.
Right. And I mean, metal machines can be quite costly. I know we're not talking about purchase prices here, but they can go up to millions of euros.
Yeah. Correct.
Yeah.
So that depends on the size and the capacity you want out of the machine, really. Looking into accuracy, the accuracy is actually really, really high. But tolerance is also really, really good. But coming straight out of the machine, it doesn't have this glossy, super high surface finish. Yeah. But it can be machined or blasted or treated to get a higher surface finish. So I put the accuracy right in the middle.
Right, because it would take some post-processing.
Yeah, exactly.
Right.
And you shouldn't be afraid of it. And that's a totally separate topic, the metal machines. But of course, you can mill and machine the parts after printing too.
Maybe we could do a webinar on metal printing.
Yeah, of course. Yeah.
If you're up for it, guys.
Yeah, I think most people are.
Right.
Ease of use. I would say it's the lowest.
Yeah.
Requires a lot of equipment around the machine, powder handling. You need to mill the part off the build plate after you print it on it. It needs to be heat treated, and lots of steps. But the quality you get out of the machine is super impressive, but it requires a lot of work afterwards.
Yeah.
Cost is high, material properties is super high. You get really high performing, super fantastic parts out of these machines.
Right. And DMLS, so direct metal laser sintering, has been around for a very long time. So it's quite a mature technology in that sense, and in terms of, the material flora, the amount of materials.
Yeah, also quite wide. Yeah.
Right. Okay. Thanks.
So to sum up this, super high quality parts. It does require a lot of post processing, very extensive preparation to get the machine working. So it's again like the HP machine. It's high stakes but high. What did I say? High stakes, high
stakes, high gains.
High gains. Yeah. We should put a patent on it.
Perhaps we should. Thanks a lot, Christopher.
Yeah.
Should we move on to the next technology family?
No. We should look into these.
Not yet. Right. Sorry. I'm so giddy today.
So there are actually people who benefit from this.
Oh, great.
So again, I would say the main benefit is for the business owner. This totally revolutionizes how you produce parts and how you set up your supply chain, but also how you design parts. So high business impact. From a design perspective, again, it allows for really amazing product designs, and a quick Google search will show you hundreds of examples of engine parts and space rocket parts and car parts that are really super advanced and super complex, super high performing. So really cool technology. From a production perspective, it's also really impressive. So you can do tooling, you can of course produce end-use parts with this technology, even though it does require some post-processing. And I wanted to bring up an example that we did in Sweden. That is an actual tool that's being run for a car company in high volume production right now. So this is, if you've seen us in trade shows, we usually bring this tool with us. So this is a stamping tool used in production for sheet metal. And then we looked into 4 metrics. So we looked at lead time for the tool, cost for the tool, weight of the tool, and also the hardness of the tool. So since it's going to be running for a long time in stamping, it needed to have a high hardness. So first of all, its lead time today takes about 8 days to produce one of these tools. With 3D printing, it took less than half of that. So 3 days, including all steps. Cost of the tool is actually still a bit higher.
Yeah,
so
slightly higher,
somewhere between 5 and 10% more expensive. But the reduced lead time usually weighs up for that. But again, it's still a little bit higher. The weight of the tool is also almost half, which makes it easier to. It requires less energy and can move faster in the stamping machine.
Yeah, and the reduced weight doesn't affect the performance at all.
No, not at all.
Right.
No. So really impressive. And the hardness of the tool, it was the hardness they have today is 60 HRC, which is Rockwell C scale. And we were able to harden it up to 57 HRC, which was more than enough to have it in production. Nice. So this is actually producing cars as we speak.
Right.
I think, but really, really impressive.
Excellent.
So it can be used for tooling as well, obviously. To improve both lead time and performance and weight.
Good.
Yeah, and that's the second powder material.
It is.
Yeah. And with that, we leave powders.
And now it's time for our next technology family, getting into the world of liquids. And Christopher, go ahead.
Yeah.
Take us through it. Yeah,
so again, under liquids, we will present 2 different technologies, each with its own benefits and users. The first one is called MULTIJET printing, MJP, which is 3D systems technology. You can see some of the parts on your screen right now. So how that works is that you have quite a big print head, and then you apply droplets onto a build plate, both wax droplets, which is the support material, the wax part you can see on your screen, and also a plastic material.
Right.
In this case, it's a wax material, which is purple.
Right.
So then you build one layer at a time, and after the part has been printed, you put it in what's called an easy clean system, which melts away the wax.
Right.
So there's very little hands-on and it allows for very complex geometries at the same time.
Right.
So how does this compare to the other technologies? Capacity-wise, it's still quite low. It's I would say a little bit higher than the FFF, the first one with a filament, but still not even close to like HP and the others. Accuracy is super high. Just to give you a small example, if we can put me up on the screen.
Let's see. Right.
So looking into the kind of detail you can get out, again, the focusing, we can. I'm not sure if it, there, maybe. It's a really nice surface finish, really nice details. You can print really complex geometries with this technology.
Yeah.
In terms of usage, this is, I would say, the easiest technology to use. It requires almost no hands-on, and it doesn't matter how complex the part is. So once it's been printed, put it in the easy clean system, melt it with the wax, and it's done.
Right. So the support material is always going to be a wax-based material.
A wax-based material that you just melt away at
a certain temperature.
At a certain, like 50 degrees or something.
Right. Good to know.
Yeah. Cost-wise, the materials are quite expensive, so operational cost is quite high, and the material properties is quite low. Since you UV cure your droplets, your parts, the parts degenerate over time, so it's UV sensitive if you don't protect them somehow.
Yeah, that's one of the big drawbacks of UV cured materials.
Yeah, exactly. Yeah. So it's more suited towards prototyping, where the life of the part is quite short.
Yeah.
But there are newer materials with better mechanical properties. So this is starting to get into 2 dots, I would say.
Right.
Yeah. But still among the worst material properties.
Yeah.
So to sum up, super high resolution, the easiest post-processing, I would say. It's quite effective at printing many small parts because it's only more or less the build height that affects printing time. The people or the roles that benefits the most from this is by far the designers, the product, the engineers.
Yeah.
So produce, low to medium amount of quality prototypes with very little hands-on. This is excellent. So this is quite a common next step for people who have used an FFF machine for a couple of years. They have gotten used to 3D printing, but they want something better in terms of capacity or ease of use or quality.
Right.
This is a great next step for them. In terms of business impact, it is quite low, but it does improve, or it does reduce lead times on projects and outsourcing costs, because the quality you can get in-house is now so good that you don't need to order parts from suppliers.
Right.
Or service bureaus.
Yeah.
And from a production standpoint, the impact is quite low.
Yeah.
It's not really well suited for production equipment or end-use parts, even though it can be. You shouldn't discard it entirely. Yeah, and there are also some cool materials you can use. So this is let's see if I can show on screen again. So this is a part that's been printed in 2 wax materials at the same time, one for support and one for investment casting. So this can be used for casting like jewelry or metal parts for industry. Really. Yeah. So that improves and helps in the process of creating molded parts. Okay, so an example from this technology is actually in production. There are many examples from product development, obviously, but from production we have a nice case that we did in Denmark, where we did an insert for an injection molding tool. So the forming surfaces and the cavity was printed. So that's the white part side of the mother tool.
Yeah.
That was printed on a MULTIJET machine. And this was used for basically low volume production or prototyping, where you needed the parts to actually be injection molded. So you didn't want to print them. So the tooling cost for this was 500 euro, even less than 500 euros actually, compared to, and all of you out there who works with injection molding, the cost of these tools, which can be really, really high.
Yes. Yeah.
The lead time to produce these inserts was about a day, 20 hours. And the amount of parts you can get out, it depends a lot on the material that you inject into the tool. But in this case, the customer's requirements was 200 parts, and we managed to get that out.
Nice.
So to be able to get 200 injection molded parts within like 2 or 3 days for 500 euros, that's an amazing application.
That's quite unique.
Yeah, that's really cool.
Okay.
Yeah.
Great.
Okay, so that's the first, I guess, liquid material.
First liquid material.
Yeah.
There are others.
There are others.
Right. Show us.
The next, and I guess the final one, it's a group that's called SLA or DLP. So in this technology, you have a resin or a liquid that's UV sensitive, and then you cure this with a laser. So that a UV laser hardens the material, and then you raise or lower the part out of the liquid.
Right. So layer by layer.
Layer by layer. Yeah, exactly.
Right.
So this is actually the first 3D printing technology that was invented in the 80s. So it's been around for a long time, and it has a really wide array of materials. And sort of like a cousin to this is called DLP, which is instead of having a laser, you have like a projector. That's one layer at a time.
Right.
So instead of, curing,
one dot at a time.
One dot at a time.
You get the whole image.
Yeah. Boom,
in
boom,
one go.
Boom, boom. Yeah.
Right. Right.
So those are cousins more or less.
Right.
Or brothers or sisters. Yeah. So SLA or stereolithography capacity is around the middle. You can get pretty many parts out of this, but it's not as high as, again, HP, which is the highest, but it's still a good capacity machine. Accuracy is the highest on the market. It's hard to distinguish a printed SLA part from an injection molded part, I would say.
Right.
Super high accuracy, surface finish, everything's great. Ease of use. What you need to do after you printed the part is you need to wash it in alcohol, and then you need to use it to like harden the surface of the part.
Right.
So it does involve 2 extra steps, which makes it not super hard but not super easy. So I put it somewhere in the middle.
And are these 2 steps, post-processing steps, are they manual or automatic? Or?
There are newer technologies from 3D systems that have automatic post-processing.
Right.
But the most common way is that you do it manually.
Okay. Right.
So you dip it in alcohol for like 5 or 10 minutes, and then you UV cure it for like 5 or 10 minutes.
Okay.
Yeah. Cost of operation is also quite low. Material properties, it has many materials, so maybe I should make this higher than 2, but and many of them have very specific like applications. So high temperature materials, transparent materials, very towards medical. You have a wide range of or a wide array of materials.
What about mechanical properties when it comes to SLA? Are there many different variations?
Yeah, there are.
Areas?
It's not as strong as like the HPs and Alto materials, but I mean it's okay.
Yeah. Okay.
But not up there with metals and the others.
Not up there among the bigger guys.
Yeah, exactly.
Okay. Yeah.
So to sum up, SLA, which is a really fantastic technology as well. If you want high resolution, low cost parts, and many materials to pick from, this is great. But again, parts degenerate over time because this is also UV cured, and you have these 2 extra steps. We need to clean them and UV cure them. So a few extra steps there.
Great.
And there are many examples since this has been around in the 80s. There are many examples out there. I just picked one. Many of you might have heard about it already. So this is dental aligners. No, sorry. The applications first.
Applications.
Yeah,
right. So,
I'm running ahead of myself.
Yeah, so did I.
Yeah.
Just love this so much. It's hard to keep track of where you are.
Yeah.
I'm just into it. So yeah, applications. Who would benefit from using SLA and DLP?
Yeah, and it depends quite a bit because SLA, since it's been around for so long, you have basically machines starting from a couple of €1,000 up to like €1 million.
Right.
So the smaller ones are mainly used for prototyping, but there are other bigger machines used for production actually. So a really good application is actually in production. So because it allows for this pretty high volume production of high quality parts, and you don't need tools. From a design, the designers love it because of the high quality.
Yeah.
It's sometimes hard to distinguish from injection molded parts. So this is just one quick example from a pretty new machines from 3D Systems. And I mean, if you show this to someone, they would almost certainly say that it's injection molded, except that they can't see the parting lines and the defects you get from injection molding. And from a business perspective, it does reduce lead time, and you can move a lot of both production and prototyping in-house and reduce outsourcing. So it has some impact on the business in general.
Right.
Then, as I touched on earlier, the example from the dental industry. This is the dental aligners from Invisalign. This is a 3D Systems reference.
Yeah.
So the amount of dental aligners, and this is instead of braces, basically.
Yeah.
So you print these aligners to adjust the teeth slightly,
Right.
and then 2 weeks later you get a new one to adjust them even more.
Yeah.
So they print now 220,000 every day.
Wow.
So that's production.
Amazing.
That's not just small volume or prototyping.
So that's really a that has pushed through with the digital transformation, digital production.
For sure. Yeah.
Interesting. Great example.
Yeah. Yeah, and that sums up the liquid materials and the third and final group.
Right.
Yeah. So the final slide really is the comparison, which might be the most important, because the goal really of this really short summary of what's out there is to be able for you to pick a technology that's well suited for you. So to go through one of each metric, one at a time, starting with capacity. If you want a high capacity machine, I would definitely go with an HP machine. That's the highest capacity machine out there. SLA, it also gives a high throughput. But if you only need prototyping or low volume production, F machine or for plastics or an ADAM machine for metals is a great option.
That would do the trick for prototyping.
Yeah. And for high quality prototyping, I would say multijet printing. That's a great way to get nice quality parts.
Right.
And in terms of accuracy, if that is important, SLA is by far the best, followed by multijet. Then the others are behind them. So depending on the other metrics, you can pick an accuracy that you need. But if that's important, SLA or multijet printing are the best.
Yeah.
And the usage, so depending on how much space you have, how much do you have a workshop, can you keep a constant humidity, do you have ventilation and so forth, how easy it is to use. If you want a low threshold machine, FFF is, I would say, the easiest. Multijet printing, it's usually a little bit more expensive. It's also a great machine. It's really easy to use. But then again, if you have the capacity to actually do this, install extra equipment and ventilation and stuff, there are exceptional, super impressive technologies out there if you have the space for it.
Right, but it's definitely something you should consider before looking at different types of 3D printing solutions.
Yeah, exactly.
What are the the physical or environmental restraints of our facilities or whatever. Yeah. Okay.
So do you have an office environment or do you have a workshop?
Yeah.
And in terms of cost, and this is again operational costs. I'm not sure if this is. I mean, if you want high capacity, you usually want low cost as well, because the cost has such a big influence. Highest among them is the metal machines, followed by multijet printing, and then it becomes cheaper all the way down to the HP machine, really, which is the cheapest per part.
Right.
And material properties, if you want high material properties, you should definitely go with the metal machines.
Yeah.
But if you only need it for like small volume prototyping, there are other machines.
Great.
So feel free to take a screenshot if you want this comparison, and feel free to contact us if you want more information or which type of machines are under each, because I mean FFF has probably hundreds of different models and machines.
Yeah, and just to reiterate, the excellent matrix that you've created here, Christopher, this can actually be used by 3D printing, people that are interested in printing and want to, take themselves further towards an investment.
Yeah.
This could be a first step in finding out, what do I actually need?
Yeah, exactly.
Yeah.
Okay. Because it is a jungle out there. It's really hard to get a hold of or grasp of what's out there and what's good for me. So I think this is a good way to start. And again, if you want more in-depth information, we have workshops. Feel free to visit our webpage where we look into the actual machines and the software and the parts, instead of just this again, this is a very broad overview of what's out there.
Yeah.
Very general.
Yeah. Okay. Excellent. Well, I suppose that rounds off
Yeah.
this edition of the Printerview.
Yeah.
Christopher Vester, thank you very much for coming to the show.
Thank you.
And looking forward to seeing you again in a new webinar.
Yeah.
And thanks everyone for watching this Printerview, the fundamentals of 3D printing. Don't forget to check out our upcoming webinars and events, local events out there. And we'll see you soon again.
Yeah.
Thank you. Bye.
Bye.